Welcome back. We're going to move into video 3 for our study of Unit 5. So with no further ado, let me get out to the PowerPoint here and we'll share. Okay, you can see that we are actually going to begin our study in section 4.2. We'll play with primes and composites as we work our way through the material in section 2. So let's go ahead and see what we can do. That's a little overview slide for us. We'll figure out whether a number is prime or composite. What's the difference? We'll look at the fundamental theorem of arithmetic. And you may have remembered doing factor trees in the past. We'll bring that back and we'll find some prime factorizations for numbers. Here's your overview for primes and composites. I like this approach. When somebody says, I need you to show me an area of 18. You can show me 1 by 18. You can show me 2 by 9. Or you can show me 3 by 6. And we would also realize then that all of those numbers could be thought of as factors of 18 or divisors of 18. So basically, if somebody says, I've got this number and I want to draw an area model, if there's only one way to draw the area model, then the number that you're considering is going to be a prime number. In this case, 18 has several ways for us to represent that area with an area model. It could be 1 by 18, could be 2 by 9, could be 3 by 8, and we will correctly classify 18 as a composite number. All right, I like this chart. It's a little confusing to read, though. What you see is the number of divisors that the numbers on the body of the chart have. For instance, if somebody says, I want to know how many divisors the number 24 has, according to this chart, there are 8 divisors of 24. And we could list them if we wanted to take the time. We're not going to do that, but I like the chart. It's a little composite kind of thing and gives us a look at classifying numbers as prime or composite. So it's for us, if a number has only 2 factors, all right, then that number is considered prime. So if you look at the column, they're almost all the way to the left side edge where there are only 2 factors. You might recognize the numbers that inhabit that column as being what you and I call primes, 2, 3, 5, 7, and so on, right? For instance, if you grab a number that's got multiple sets of factors, more than 2, then we'll classify that number as composite. For instance, 16 has 5 sets of factors, 5 sets of divisors, so it will be classified as composite. So this is just a little look out at that type. All right, the ones in the 2 positive divisors are going to be considered primes. The ones that have multiple positive divisors, more than 2, are going to be considered composites. And one's the odd duck. One's neither. We don't classify the number 1 as prime, nor do we classify it as composite. One has only 1 factor. So it's just kind of left out at the party. It doesn't get to be part of the prime package, nor does it get to be part of the composite package. All right, this is just a summary slide. Basically, you can read through it. It says it's prime if it's got only 2 distinct factors, the number itself and 1. Some examples for you, 2, 3, 5, 7. 2 special when we discuss primes in that it's the only even prime. All the other numbers that we'll consider prime are odd. Now, that's not true that every odd number is prime. For instance, 9 is odd, but 9's not prime. 5 is, 7 is, 11 is, and I won't impress you with my prime knowledge. All right, again, in green, 1's the odd duck. It doesn't get classified as prime or composite. I just realized I didn't send you into, yeah, try here. Okay. All right. Well, now, I have to tell you, the answers are going to be a little weird here. So the problem says, why are these numbers composite? And basically your premise is there a number other than 1 and the number 1,566 that will divide that? And that's what we're asked to find. So look, I think for most of us, we're going to say, oh, you know what? It ends in 6. It's even. So 2 divides it. Well, that's it. That's all I need. So you might not come up with the exact same answers here because I tried to show off a little bit. I went even on this, so it's divisible by 2, and that means it's not prime. That's why it is composite. It's divisible by 2. All right, well, shoot, that one doesn't look divisible by 2, but you know what? If we add the digits, 3 plus 3 plus 5 plus 1, we get 12. And remember, if 3 divides the sum of the digits, then 3 will divide the number. So you guessed it on problem number 2, 3 divides 3,351, and that would be enough of a justification for that being classified as a composite number. Look, I'm showing off, but you know what? That thing ends in a 4. It's even. It's divisible by 2. That's perfectly fine. I tried to sneak in the divisible by 4 idea. All right, you look at the last 2 digits, it's 24. 4 divides 24, so 4 will divide the number 8,524. Either method would have been good. All right, either method would have been good. I just went after the 4 just because it was something different. Oh, baby. Well, again, it's even. It ends in an 8, so it's divisible by 2. That's enough. What's Dale going to do? He's going to be high tech, and he's going to grab the last 3 digits. He's going to say 888 is divisible by 8, so that number is divisible by 8. But that's not the only good answer. You could have said, well, geez, the last 2 digits are 88, and that's divisible by 4. So that number is also divisible by 4. So you have options on this. You're just trying to find something that you know will divide that number other than the number itself and 1. All right, what do you think here? 2 times 3 times 5 times 7. And then just for fun, we're going to add 5. Well, if you don't add 5, all right, if you just say 2 times 3 times 5 times 7, that's definitely going to be a composite because 2 would be a factor, 3 would be a factor, 5 would be a factor, so would 7, so would 15, so would 14. And you and I can get factors by multiplying any combinations of those 2, 3, 5, 7s. But if you let me add 5 to that product, then I think I might be able to convince you that 5 will divide that piece of arithmetic in front of you. So I think 5 is a factor, and that means that given number is in fact composite. Okay, prime factorizations. You probably have done factor trees in the past. I've worked with different teachers, different students on this, and some teachers teach in that you must break only into primes as you begin. Technically, you just have to make sure that at the end you have all primes, but you don't have to have primes the whole way through the journey. So I can give you some freedom and some flexibility. I think most of my examples, I probably do try to grab a prime. The other convention you'll see on the PowerPoint is when I identify a factor as prime, I tend to circle it so that later on when I try to write the prime factorization, I just don't lose them. Particularly if the numbers that you're busting into prime factorizations are large, it can be a little bit easier than you might wish to lose some of your primes. Okay, here we go. So the challenge is, can we find the prime factorization for 100? So I said, all right, here's 100. And again, if you want to grab a prime first, you could grab 5. I think most students probably see, oh, good, it's even, so they'll bust it out with a 2. So you say, all right, I'm going to break that down. It's going to be 2 times 50. Now, I do believe 2 is prime, so I'll circle that. All right, so that's cool. 50, I don't believe is prime, so I'll continue my journey. So what do you got for me? Well, again, I'm probably going to grab a 2. Could have grabbed a 5. All right, I'll grab a 2. 2 times 25. Yep, 2 is prime, so I'm going to circle that. 25's not. So I'll keep busting down the 25, and you guessed it, it's going to be 5 times 5. And it just so happens that both of those 5s are prime. So it looks like we got everything we needed. We have now found the prime factorization for 100. It contains 2 factors of 2, and it contains 2 factors of 5. And I often do write those with exponents attached. So 2 to the second times 5 to the second. Successful prime factorization by using a factor tree, okay, for 100. Fundamental theorem of arithmetic basically says you pick the number, whatever you pick, it has the unique prime factorization. Again, we should probably agree that that doesn't depend on the order in which you write the primes. The general consensus is you write the primes smallest to biggest, but every number that you pick has a unique prime factorization. That, my friends, ends video 3. We'll be back soon with video 4 from Unit 5. See you then.